So let's compare this summary of astronomical observations with hypothesis of Torrey. So we thought lower temperature brighter, and we may suspect and find that maybe it is opposite. So here is the collection of the famous stars. We will not do little entertainment right now, but one can go onto the night sky and identify stars and see what are their colors, and they are different. Like Rigel is somewhere in our favorite or Orion. Here is the sun in the middle, and the x-axis is temperature, y-axis is intensity. So the lower the temperature, the lower the intensity. So it's opposite to this hypothesis. Make sense? Well, if you believe this chart, which we do not need to do, we may need to do astronomical observations ourselves. And as the color of the star, as the temperature of the star increases, it gets more intense. Okay, and at the same time, there is a this chart is like oversimplified, is only demonstration thing, but it shows connection between color and temperature, right? So lower temperature, red color, high temperature, blue color, and mixture of colors like white in the middle. Okay, let's look to the this little thing that we are exploring. Oh, no. I just want to bring it to the very beginning. Okay, so if you look this video at the very beginning, it shows the summary of the Planck formula for blackbody radiation, and it's not labeled, but the x-axis is wavelengths, y is intensity, and it has a peak. This is done for temperature of sun of about 5,000 Kelvin. And next few snapshots at the very beginning. Yes, here. You saw the line goes to the right and changes the intensity. So let's do it. Let's find the same thing online. In addition to stars, just look for also in graphical form. So there are multiple demonstrations. Online. So what we see, and here the colors I'm misusing. They are not smart. They use like cyan for something at the border of red and infrared, but this line should be yellow and like greenish yellow, and then going like orange and more red. So when the temperature decreases, we have less and less intensity, right? It is one trend. And another trend that the midpoint, let's check if there is a annotation option. No, it will take too much time. So if we look onto the position of the peak, we see that as temperature decreases, it moves more and more to the infrared, right? Or if you go to increase of the temperature, it goes from infrared and red more to the UV. This will be a part of your homework due on Wednesday in class, and you shouldn't be discomfortable or scared. It is much simpler than things that you did before. So look at the data that we collected last Monday and identify based on the spectrum what was the temperature of the filament. And there is a mathematical equation for this line, and it explicitly includes the temperature, right? So our goal is to get as far as possible into reproducing and understanding this equation. Okay. So running. Instead of preparing nice slides, I was trying to program this code because it consolidates the idea behind the Blackbody radiation. So what did we discuss last Monday when we were doing some equations together? Probability of PL. Okay. So amount of energy stored in one, which object? Huh? No, 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 no. Let's jump. So we started from geometric progression, and then partition function for applied to what? Which model? Of Boltzmann distribution applied to what? The favorite model of partition. No, 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 not normalization is a concept, but model. There are natural objects and there are mathematical models, like two-level system, like hydrogen atom particle in the box.
Harmonic oscillator?
Yes, harmonic oscillator.
Yes.
I knew that she knows. Okay, so harmonic oscillator. What is the connection between harmonic oscillator and Blackbody radiation? I know this question is not easy, and it is a like foundation of all modern science that people were trying to figure out for many years. So if you do not have immediate answer, it's completely normal. Test. Okay, it works. So what is the connection between harmonic oscillator and blackbody radiation? So suppose I am an ancient blacksmith having flames from the coal to hammer a sword, and then when it is heat up sufficiently, it glows in the dark. So what is happening? What is the connection between this piece of metal and radiation?
It's like hitting it starts putting off radiation.
Yes, and metal doesn't have band gap, doesn't have specific structure. It has just field orbitals, field and unfilled, and there is no offset between them. But by some mechanical way, or some practical way that we do not care right now, the sword is passing on quanta of different frequencies or wavelengths into a little area of space. Like the whole space is chopped on like little blocks, and we can hypothetically assume that these boxes are filled with this box. The box is filled with, there are no molecules, it's just free space. Let me bring you a blacksmith in a vacuum. It will glow in the dark same way, right? Light, yes, light. And what is light? But if we have like a mirror, and we know that an electromagnetic wave is captured between two mirrors. Huh? Just I didn't hear. Just repeat. Excitants deal with matter, and when light is not excitants. So electromagnetic radiation between mirrors. What is it? Yeah, standing waves. Okay, so it's like either half wave, or it can be like full wave, or same like particle in the box, like box and then electromagnetic waves inside. What is this? What deviates from equilibrium? What, like if here I put x is length, what is y? Intensity of what?
Like the energy wavelength.
Not energy, but starts with letter E. Yes, electromagnetic field, or if we neglect magnetic interactions, we can say that just projection of electric field, right? Of X. So it is bigger in the center and smaller closer to the edges, and it can have more updated shapes. So what is the common, so electric field? Electric field. What are those shapes? Like, huh? If you come with the drink, like glass of wine, to your laundry room, and let the drink on the washer when it works, what do you see on the surface? What's the scientific name for it?
I said some time before. I said interference. I don't know.
Okay, yes. Other options? field. So
Aren't they just standing waves?
yes, exactly. Everyone agrees? Okay, standing waves in the laundry room and standing waves of electric field inside the resonator. Right? Okay, electric field, standing waves. Lambda over 2, lambda, 3 lambda over 2, and they will have different frequencies. Now, electric field cannot just change over time and be like at maximum. It oscillates, right? So it oscillates with the frequency lambda nu equals speed of light. So nu is speed of light divided by lambda, right? So the size of the resonator determines the frequency. And then it oscillates. So at each point of space, x comma e of x comma t. So for given x, it will be a sine omega t. It will oscillate. So electromagnetic field inside the resonator oscillates, right? And if you have all standing waves, each standing wave can be considered as what? Something that oscillates can be referred to as
A standing wave?
no, an object that oscillates. We do not need to be scientists. We can be linguists, like analysis. A thing that oscillates is an
Oscillator.
oscillator. Yes. Okay. So we do have a box. Like here is a one-dimensional box, but in fact, we do have three-dimensional box, which is packed with many oscillators. And there is no heresy in this. It's just if we chop space on smaller regions, we can assume standing waves there, right? And harmonic oscillator is something that we can treat both quantum mechanically and statistically. The feature is that there are many oscillators. And let me make a shortcut before we go into too many equations. So I will reproduce what we had on the movie. So this is a Planck formula for BB, blackbody radiation. And there we had a stream of little peaks that were reappearing at different wavelengths. And then we accumulated stuff like this, intermediate line. You remember, right? So each oscillator is able to emit light. If it is in thermal equilibrium, it can absorb and emit light. But different oscillators, different standing waves, have different frequencies, right? And each of these standing waves have different statistical equilibrium state. Because they have different frequencies, the Boltzmann distribution for those objects has different values. So we have a box filled with oscillators, and each oscillator emits light at its own frequency with its own intensity, right? So we can say that oscillator with wavelength lambda has intensity I of lambda, right? And just mathematically, we can make the width finite width, but the individual peak can be described as delta function lambda minus, let's put it lambda prime I of lambda prime. So this will be an individual peak. And if we put an index for each oscillator, then overall spectrum will be summation. So overall emission of all lambda will be summation of individual contributions of little delta functions, like contributed by individual oscillators. Let me slow down and walk and ask for your complaints or discomfort, because I see how smiles dissolve and change into opposites. So sorry, what is this summation of contribution of individual oscillators?
I'm fine with it now. I'm just trying to connect everything based on the video we watched.
Okay. Patricia?
I just wanted to ask that the lambda minus the lambda is the total lambda, right? The first one, okay.
Benjamin, any objections or questions or discomfort?
I'm just not this comfortable with math.
But like you may not like delta function, you may not like summation or it's my duty to explain. Huh? Okay, I'll collect the question and we'll answer in a minute. Rebecca.
Are you saying it's a summation of like each spot in that one peak or like all of the peaks?
All of the peaks.
Okay.
Max, I'm fine with delta function.
I don't really know what a delta function is necessarily. I just thought it was like a difference between two values, but I don't know.
Okay. So can I count on your enthusiasm if I tell that you have fewer peaks here and much more peaks in the middle? If we add them together, they may create some average shape. So intuitively, you're okay. And if you convert this idea into here, it's also intuitively okay. You're just not comfortable with delta function. Delta function is a mathematical concept that corresponds to infinitely high peak centered when argument is equal 0. Lambda equals lambda prime. And main property, there are a couple of properties of delta function, like integral will be 1. So it's infinitely high function with the area with infinitely small width with integral under the area under the curve equals 1. If one changes limit of integration to certain value, it will be 0 if lambda 2 prime is smaller than lambda prime, and will be 1 if lambda double prime is bigger than lambda prime. So as we move along the curve, the result of integration changes from 0 to 1. And Adam is not here today, but you remember that Adam taught us the equations of like snake and the rabbit, right? So snake and rabbit were expressed for the Kronecker delta for matrices, but now we are dealing with continuous functions, and instead of summation, it's integration. And the integral and delta function d of some variable again, cancel each other and get into a number. You see connection. It's like Dirac delta and Kronecker delta, but they have similar properties. And practically, you do remember Gaussian distribution, the bell shape, right? So I do not remember it exactly. It's something like square root of 2 pi sigma e minus lambda prime squared divided by sigma squared, something like this, right? So in the limit of sigma, the width parameter and delta sigma going to 0, Gaussian function is considered as delta function. And if we didn't exactly manipulated this width parameter to 0, then we will have this finite peaks that are look not infinite, but some finite width and finite height. Okay. So did it address your curiosity about delta function? Okay. So this part is absolutely missing in all textbooks, but I just reviewed and thought that without this concept, the canonical part of the blackbody radiation material will not connect to anything in our style of thinking. So now our task is to identify how many delta functions, how many oscillators are available in a certain interval of wavelengths, and what is the intensity of oscillator of a certain wavelength. Okay? I know it is a little silly, but I write concepts just by text. How many oscillators are available in a certain interval of wavelengths or frequencies, like from lambda to lambda plus delta lambda, or frequencies from omega to omega plus delta omega. So it's question number 1. And question number 2, for given lambda or frequency, wavelengths of frequency, what is the intensity of emission of a single oscillator as function of temperature? So if we do have answers on these 2 questions, we can practice our mathematical skills and get this distribution of solar radiation or sword radiation or Sirius radiation. When we met here a week ago, we did answer question number 2, and it will save me a lot of time. I'll try to skip interviewing and going back to derivation, but we have derived together that average energy, so intensity of oscillator of a given frequency, is proportional to average energy stored in the oscillator. And by using statistical mechanics concept of partition function, we've got that it will be frequency divided by exponential of frequency divided by Boltzmann times temperature minus 1. Does it look similar to what we've got a week ago? Please catch me if you can. We better fix errors now.
I didn't have it as omega as instead of omega, it was energy.
Yes. Omega is energy.
Oh, okay, that's frequency.
They like H bar omega equals energy.
Oh, there's still the H bar factor.
Huh?
There's still the H bar factor. That's different.
Yes, in atomic units, H bar factor is 1. Okay, let's put proportion. But there is sign is correct here, sign is correct there, right? Questions? Rebecca, does the plan looks reasonable?
Yeah,
It agrees with what we were deriving last time?
is this not, is it not, I don't know.
Yes. So to be a little more precise, H bar and 1 over KT is denoted beta by statistical mechanics people. So equals H bar omega E H bar omega is beta minus 1. Benjamin, please confirm. Yeah, confirm. Oh, yes, please.
I don't know if it's very silly, but I do not know why you remove the equal sign and put this. Is it that it's not the approximation sign? Like it's not totally equal to that.
So you do not like style like place material on the whiteboard. So those are little comments, definition. Here is the equation, equals this way.
You know, initially you put equals to here, and you don't change what's with it.
Yes, because I was scared by maths. It was like, where is your H bar constant? Oh, no, I don't know. Proportional, it means like you can put an arbitrary factor in front. Okay. And right now we don't care by absolute value, we just need trends. So you don't want to take too much responsibility for exact factor. So we are on the same page, and we are 50% done a week ago. We just need to consolidate these two things. So this one is done. And now we need to answer how many oscillators are available in a certain interval of either wavelengths or frequencies. I'm going to, yeah, it records approximately up to here. I'm going to erase the board and start over, but you have your notes and we agree on this plan, right? And as soon as we have these two things, we can return back into this equation. And in fact, if we would know that at certain wavelengths there is more than one oscillator, there is a degeneracy factor. Like if there are more than one, we can call it G of lambda prime, right? If you know that for certain wavelengths there is more than one oscillator, then we can literally follow this equation and get Planck's constant. So I would say that the first question requests us to find the degeneracy factor. Degeneracy factor. Or some people, Tori will be surprised. You know the next word, but you never convert this how many. Please try. How would you call how many oscillators are available in a given interval or degeneracy factor? If instead of oscillators of electromagnetic field, we would speak about states of electrons in a like molecule or in a solid. How this definition can be converted Which terminology would one use? Multiplicity is more for spins. No, if you have like many orbitals at certain energies, and some of them are dense, some of them are sparse, and you have energy on X, and what is on Y? Density of states, DOS. So another name for this degeneracy factor on number of oscillators in a given interval is density of states. But with understanding that now we are speaking not density, not electronic states, but density of photon states, of electromagnetic states. So our goal for whatever time we left is to find density of photonic states, degeneracy factor, number of oscillators in a given interval. And it is one of the reasons why we, and it's Benjamin told that there are more states in a certain range, less states in another. Yes, correct. As we go more to the UV range, we get the density of states will grow and it will become more and more states. But they become less and less populated. So there are two factors. So we cannot speak that only one of them works. There are two factors. And this factor, which was more, second factor, which was more challenging and unusual, we already done with it. This factor number one was more or less standard way for scientists of 19th century to consider, but it is a little more laborious. And if we do not do it every day, then we'll need to concentrate a little bit. Okay. Do I have your permission to erase basically everything? Okay. Or maybe I'll leave this part as a reminder for myself and start playing in this area. Maybe I can copy paste these equations that we need to practice at the very end. So intensity of lambda is either summation or integration. Intensity of individual oscillator, delta function, and then degeneracy factor G of lambda prime. Okay. Oh. Some people call 1 over lambda as a wave vector. And if we do have electromagnetic wave going into like three-dimensional direction, not along X, Y, or Z, but has three components. Like if we have direction of electromagnetic wave decomposed over Kx, Ky, and somewhere Kz, where each of the projections is can be associated with certain wavelengths, then the length of this K vector is Kx squared Ky y squared k z squared, and the frequency corresponding to this vector will be absolute value of this wave vector times speed of light. And the wavelengths will be just 1 divided by the length of this a vector if you need it. Some of you, at least Adam, who is not here, went to similar exercise for particle in the box. Patricia, did you for three-dimensional particle in the box? Were you in the class at this time? Okay, but there is a difference, like for electronic states. Energy with 3 quantum numbers in x and y and z is proportional. Okay, I will be again taking less responsibility. Nx squared over Lx squared plus Ny squared Ly squared plus Nz squared over Lz squared. And if I want to be exactly, it will be something like h bar squared over 2 masses. So for material, for electronic waves in a box, the energy is proportional to square of the quantum numbers. Here, we will introduce analogs of quantum numbers associated with these wave vectors, but the dependence of frequency, like if we multiplied it by h bar, without bar, if it is h times nu or h times k, it will be energy, right? So energy will be h c square root of ax ay az. So instead of summation of squares, it will be square root of summation of squares, because electrons in a matter and photons in a space have different fundamental laws, and therefore density of states for photons will be different than for the electrons. We need what my goal is to find that this density of states or degeneracy factor, if we find it as function of frequency, will be, okay, less responsibility, proportional to omega squared. While for electrons, it was square root of omega. So this is common for Patricia and Adam, if he watches. So the density of states for photons is different than density of states for three-dimensional blocks of electrons. Now, how this density of states can be derived? I apologize for the pause. I have very clear mind. I'm just trying to convert words, thoughts into words. When half an hour ago, I drew this one-dimensional resonator with half wave, full wave, and 2/3. We can say that here is lambda over 2, and the wave vector in this direction will be equal 1 divided by lambda over 2. Here, the wave vector will be 1 divided by lambda. here wave vector will be 1 divided by 3 lambdas over 2. So if we continue, let me just keep this here. See? So how do the K vector change if we increase, if you go from from longer wavelengths to shorter wavelengths? Do you see my error? So additional credit to anyone who observes an error, and I have already identified it. So as we go from longer wavelengths to larger wavelengths, the wave vector will be increasing. Wavelengths becomes shorter, and the wave vector becomes bigger. So those things are doubtful, but this is correct. Please express any objection on this statement. So if you go to shorter wavelengths, our wave vector becomes bigger, and it goes in integer multiples.
Ask someone else. I'm still thinking about it.
Okay, but please bring any confusion or discomfort. We'll resolve it together. Now, if we admit that for shorter wavelengths we have bigger wave vector, we need to take into account that our wave vectors, our standing waves, are in three-dimensional box, right? Three-dimensional box is a little less illustrative. I will go to two-dimensional box first for telling the story, and then we'll upgrade two-dimensional to three-dimensional. And now we come to the area that is available in most textbooks. So we have kx, ky, and then we can have values of k, like kx divided by minimal minimal value of the wave vector, it can go in the progression 1, 2, 3, 4 by integers. Same for the y. So a state of standing wave in the square two-dimensional resonator is fixed by two integer numbers, which are analogs of quantum numbers, kx over k naught and ky over k naught. So a point on this diagram means one standing wave. So we have kind of square lattice of points. Now we do need to identify, are there standing, and each standing wave can get its like wavelengths, frequency, energy based on these numbers, like two numbers, and for three numbers it just will be bigger lattice. So the question is, are there more than one standing three-dimensional standing waves that do have the same energy or very similar energy? So are there more than one standing waves with the same frequency? So the energy of a standing wave is a square root of sum of squares, right? What does it mean geometrically? So it means distance from the origin to a certain point. So it will be kx squared plus ky squared square root. Agree? And now we need to decide, are there more than one states, for example, like 5 and 2. 5 and 2. If you have 5 and 2. Would this standing wave have similar or different energy compared to this one? So this one is kx equals 5, ky equals 2. Here, this one would be kx equals 2, ky equals 5. So if you practice the equation, square root of 5 squared plus 2 squared, here it will be a square root of 2 squared plus 5 squared. Like 5.3. Is there any difference in the length of these two vectors? So we found that well, there will be more, but we found that at least two standing waves have the same frequency, right? And this is the main goal of our meeting. We just need to bring more regularity in this consideration. So we need to find how many degenerate states appear at a certain interval of energy, which means we need to encircle all states that have distance from, that have frequency from this one to something a little bigger, and catch how many points fit into this ribbon. Make sense? So if this is two-dimensional exercise, what is the area of inside a circle? Pi r squared, right? Okay. And if it is a quadrant, if we have only the quarter, because in numbers are integer, then we divide by 4, right? So it's like 2D. If you have the same box in 3 dimensions, what is the volume of a sphere of a radius r? 4/3 pi r cubed. Okay. And if all x's have only positive values, then instead of quadrant, it will be octant. We chop twice, chop twice, chop twice, 2 to the power 3, 8. Right? So the volume, the amount of states inside certain range can be computed by this middle school equation, right? The radius here has meaning of this radius has meaning of energy divided by h divided by c, right? Speed of light, or just frequency divided by speed of light. So we can say it is number of states inside that have energy between 0 and not omega, should be regular frequency, between 0 and frequency mu will be this much, and here we put mu over c. Okay. If by some reason we like angular frequency, we can replace mu by omega by 2 pi. Right? 1/8 of thirds pi omega 2 pi power 3. And we will be able to cancel several factors. Now, if we need to find the amount of states in the range between nu and nu plus delta nu, we can call it as density of states as function of nu, and we can define it. Let me do it carefully. Number of states up from 0 to nu plus delta nu minus number of states up to nu. And we can multiply and divide by delta nu. So by mathematical liberty, we can multiply and divide by the same factor. Now, in the limit delta nu goes to 0, what does this brackets correspond to? How can we name it based on calculus 1? I'll just slightly rewrite. So delta nu will be here, and outside of the brackets, I'll put delta nu times limit delta nu goes to 0. So limit of increment of function in respect to increment of the argument. Let's check how you were performing calculus 1. So what does the definition correspond to?
As delta nu approaches 0, something is going to happen to that function, but I do not remember limits.
So mathematicians are different from natural scientists. They do not rush to find solution. They just prove that solution exists, or they give names to solution, or prove some properties, theorems. So I'm not asking what it is equal to. From mathematical point of view, what does it define? How would you call this definition? Limit, I can rewrite it in a different way. Like y of x plus delta x minus y of x divided by delta x. Okay. If you have a function y of x, we connect 2 points, right? And we divide y of x plus delta x, y of x plus delta x. So how does this line is called? As function changes, this line will be changing its orientation, its value. Okay, tangent, slope, right? But more advanced mathematical name. Starts with letter D.
Derivative?
Yes, you passed. You got A in calculus. Okay, everyone agrees? So derivative. So we do have derivative of number of states over the frequency. So delta nu d nos divided by mu, right? And this definition is needed because if we do have mathematically well-defined function and we do have procedure of derivative, we can just apply it, right? So if frequency comes here into the third power, what does derivative makes to the polynomial function? It decreases the power, right? Like derivative of x to the third will be 3x squared. So if I want to process this version, so I will keep, I'm just fearful of missing factors, but we will cancel things right away. So pi 1 over speed of light third. And now the only thing is mu to the power 3. And after derivative, you have 3 mu squared, right? This is the only derivative for today's meeting. The rest were just philosophical considerations. So now let's figure out 3 cancels with 3. 4 cancels with 8, leaving us 2. And then we do have pi 2 c cubed mu squared times delta nu. So this is density of states, density of photon states as function of nu. If we want to express it in terms of the angular frequency, we just accumulate 1/4 pi squared in the denominator. Then do the same. Pi 2 c cubed omega squared, and pi square is cancelled. So it will be 1/8 pi c cubed omega squared. So either one of these equations is answer to number one. Okay. And now we do need to practice to combine these two equations into something like this. Here is integration over lambda, but if you feel more comfortable with omega, the mass is similar. Omega prime, omega prime, g of omega. So we do have this degeneracy factor, which is just omega squared 8pc cubed. We do have delta function, and we do have the intensity, which we believe is this this factor. And there is an additional trick that if we need the emission at a certain interval of energy, if we need instead of integrating the emission of certain wavelengths, needs to add another derivative, and another derivative will compensate this integration, and as a result, one would need just a product of this of these two functions. So if one carefully processes this trick, then it will be per omega e h bar omega at minus 1. So we do have factors. This will be black body radiation intensity as function of frequency, and then we have it's proportional to cube, has speed of light, and has Planck constant. So this function has two trends. One trend that as I'll focus on this range, just in case any of us wants to watch the recording. So there are And we are doing very good with time. We are going to finish very soon. So as frequency increases, we have higher density of states. But each of the density of states of oscillators, right? At higher frequencies, there are more and more oscillators. But probability that certain oscillator will emit decreases. Oscillator emit weaker. And second trend, as frequency decreases, we have less states, less oscillators. So it is lower density of states. But due to this statistical factor, it emits more vividly. So it's a higher probability of emission. Higher intensity of each oscillator, of individual oscillator. So Blackbody is a concept that considers area of space that traps a lot of oscillators, quantized oscillators of electromagnetic field. Each of the oscillators absorb and re-emit light. Each of the oscillators are in a thermal equilibrium. It's important. And because of the thermal equilibrium, the emission of each oscillator depends on ratio between frequency of oscillator and temperature, right? So UV oscillators, higher frequency oscillators emit weaker. Infrared oscillators, low frequency, emit stronger. But the density of states grows quadratically, and these competing trends produce a function with a maximum. But the position of the maximum can be fine-tuned by the ratio between frequency of oscillator and temperature. So by manipulating temperature of a realistic sample, one can make it to not only emit stronger or weaker, but one can also tune the frequency or wavelengths at which this emission has a maximum, right? So on one way, it is a spectacular way to think about stars, like blue stars, red stars. On another thing, this is universal law that applies to any object in a thermal equilibrium. So the concept of Blackbody means that if this box of photons is brought into vicinity of any material, no matter of its composition, it will behave in the same way, right? So if an object is in thermal equilibrium, its emission will obey the Blackbody radiation. The light-emitting diodes are not in the equilibrium. Lasers are not in the thermal equilibrium. Therefore, they have narrow emission lines. Excited molecules are not in the thermal equilibrium. But if thermal equilibrium means that the excitations and de-excitations compensate each other, so that for each of these oscillators, amount of energy in and energy out at each frequency is equal. So this laws of Blackbody radiation can give practical means of measuring temperature. Specifically, by connecting this equation to experimental data of any Blackbody emission, one can reconstruct what was the temperature. And this is the homework for the our next meeting on Wednesday. So I did send the numerical data collected there, where intensity is a function of wavelengths. and it is done for 3 different voltages of the for this filament, and they look like as expected. Or 140 volts, or about 100 volts, and completely going this way for 65 volts. And the question is, what would be the temperature? I would assume results would be something like 4,000 Kelvin, 3,000 Kelvin, and maybe 1,100 Kelvin. But it is a very rough estimate from the top of the head. If you try to compare these lines with this equation, and another code I did send provide this thing, or you can do it yourself, you can get a little better values, and maybe describe how do you observe it. What else? The major benefit for modern science is that of this Planck equation is that it was a very first work that did assume quantized energies of oscillators. That was not part, like if you deal only with number of states, density of states, we do not care about quantization. But in the second part, we did both quantum and statistical. We assume that we put our foot into the door of new area of science. And this concept of thermal equilibrium is more and more important if you want to deal with ensembles of many molecules in your solvent. So this statistical approach is more and more valuable if we go from properties of individual molecules to properties of ensembles. On Wednesday, I will try to give another example of application of this statistical mechanics, and then I think we will be done with my part of the class. The fun fact that Planck constant was defined by fitting this equation to spectrum of sun, which is non-experimental. So this several digits of Planck constant, it's just experimental fit. So any objections or questions? Do you think this little task is doable by Wednesday? Yes, send me emails if you find it too challenging, but I think it is much easier to many things that you did in the past. We do not have time to make presentations because time is over because of several circumstances, but maybe I will design one more homework that will be counted as an exam towards this part. So to have this first part of the class done. Okay, so if there are any questions, feel free to formulate. If no, meeting is done, everyone is welcome to depart and disconnect.